Do you like your process data smooth or chunky?
I have no idea what any of that means.
Is your process data spread smooth or chunky? The full story is an episode of the Degrees of Freedom project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. Presentation and analysis of process data from chemical and thermal processes is one of the fundamental activities for process engineers. I will review and explain some of the most common techniques. We assume that you are familiar with basic statistics and linear regression. If any of the subjects seem unfamiliar, please go back and view the statistical technique videos in the link in the description, such as How Deviant and Mean Are Your Data, parts 1 and 2. Do you like your process data smooth or chunky?
I have no idea what any of that means.
I would say smooth, but I'm not sure what the difference is.
Smooth.
I'd assume smooth.
Often, when you're collecting engineering process data, you end up with sets of data that come in pairs, a dependent or measured variable and an independent specified or set variable. For example, a set of pressures is a function of temperatures, or a set of flow rates is a function of time. We assume some functional form for the relationships among the data pairs. We represent this relationship with the dependent or measured variable y as some function f of the independent or set variable x. Anytime you have actual collected data, there will be measurement uncertainty, if nothing else, then from the quantization error. Also, many processes have a bit of variability in them, so even if you could measure exactly, you often see variability due to the process. Because of the uncertainty and variability, the measured y value for a given pair is going to consist of the true value of y plus the error or residual, depending on what mood you're in, for that particular measurement. In other words, we have the true functional value at x sub I plus the error epsilon sub I. The question is how to determine what this f of x is and what the uncertainty in the parameters of f of x is. When looking at a plot of experimental data, which is the easiest for you to see? A straight line, a parabola, or an exponential curve?
Probably a straight line.
Definitely a straight line.
A straight line.
A straight line is easiest, but I feel comfortable seeing all of them.
For determining the functional forms of f of x, it turns out that the human visual system is very good at seeing if the trend in a plot of data is a straight line or almost a straight line. If your data plot doesn't appear as a straight line, it's possible that a change of coordinates will make it appear as a straight line. The most common change of coordinates in engineering data analysis is from a linear data plot to a logarithmic plot. There are also many other transformations that make a function appear linear. Let's examine the functions that appear linear with a change to logarithmic coordinates. The table lists first the original function, then the transform that changes it to linear function, and then the coordinate scale to obtain a linear plot. The first function is the equation of a line, y equals bx plus a. And obviously, since it's already the equation of a line, the linear form is y equals bx plus a. A brief aside, the equation of the line is not actually a linear function, since f of c1 x1 plus c2 x2 doesn't equal c1 f of x1 plus c2 f of x2. For a linear plot, you plot x on a linear scale and y on a linear scale. What's the difference between a semilog and a log-log plot?
I have no idea.
I guess a log-log plot is probably a log of a function, but I don't actually know.
Such a good question. I'd assume a log-log plot. Actually, I have no idea. Just disregard that.
A semilog plot will have one of its axis variables operated with a log on it. A log-log plot will have both of its axis variables operated with a log on it.
The next function is y equals a times e to the bx. The linear form comes from taking the logarithm of both sides. You end up with the natural log of y is equal to the natural log of a plus bx. A plot of natural log y versus x has a slope of b, and the intercept is the natural log of a. If you want the value of a, you would take the exponential of the intercept. For a linear plot, you plot x on a linear scale and y on a logarithmic scale. This plot is often known as a semilog plot. Because e to the x and 10 to the x differ by a simple multiplicative constant in the exponent, we expect 10 to the x to behave the same as e to the x does. If we take the log base 10, also known as the common log, of both sides, we get a log base 10 of y equals log base 10 of a plus bx. A plot of common log y versus x has a slope of b and an intercept of common log of a. For a linear plot, you plot x on a linear scale and y on a logarithmic scale. This plot is also often known as a semilog plot. Finally, we have y equals ax to the b. This is known as a power law relationship. If you take the logarithm of both sides, you get the log of y equals the log of a plus b log x. I have not specified whether it's a natural log or common log because both equations come out exactly the same. A plot of log y versus log x has a slope of b and an intercept of log a. For a linear plot, you plot both x and y on logarithmic scales. This plot is also often known as a log-log plot. Besides these three, there are many other ways to plot data to get straight lines, depending on the functional relationships, but these are the most common. So here I have a matrix of plots, and I want to show you what different types of data look like on these different types of plots. Starting with linear data on a linear plot. You will just see a linear line, straight line, on a linear plot. For linear data on a semilog plot, you'll see a slightly curved line, like this. And then for linear data on a log-log plot, you'll still see curvature upward like this. For semilog data on a linear plot, you'll see something that looks like an exponential function, something like this. And then for semilog data on a semilog plot, you'll see a straight line. And for semilog data on a log-log plot, you will see a slight curvature, similar in direction to the exponential, but less intense. For log-log data on a linear plot, you'll see something very similar to an exponential curve again. And for log-log data on a semilog plot, you'll see opposite direction curvature. And log-log data on a log-log plot, you'll see a straight line. There's a spreadsheet on the DOFPro website that shows simulated graphs of all of these with data that you can reference. We have not discussed how to do a linear least squares fit because most people know how to perform one. Review the linked videos if you don't. Spreadsheets have built-in functions for linear least square fitting. For example, in LibreOffice, you can get the slope by using the slope function, and you can get the intercept by using the intercept function. You can also simply just choose a data fit on the plot itself. The plots also have the choice of an exponential or power law fit as well. These work reasonably well, even for the transformed coordinates that we've discussed. There is a subtlety that comes from data fitting the equations that are transformed to make them linear equations. When you transform the points, you also transform the errors, and so you are no longer fitting the original function. In other words, fitting log y equals log a plus b log x is different from fitting y equals ax to the b. Depending on how you do the fit, you may end up with different values for a and b. If the data are good, the values of a and b will not differ much. But if they are not, you definitely want to choose which one to fit, and it's likely that the errors fit the y equals ax to the b function better than the log y equals log a plus b log x. There is a later video that explains how to perform nonlinear least squares fitting using a spreadsheet. The link is in the description below. For the moment, I want to give an overview of how it's done in case you want to get a head start. For the y equals ax to the b function, and for a dataset with pairs of data, you would start by guessing values for a and b. We will call them a fit and b fit. Those are the fitting parameters. For each data pair, you would calculate the y sub I fit as your guessed a fit x sub I to the b fit power. Next, you calculate the error or the residual as the difference between the fit value and the measured value. Next, you calculate the SSE, which actually stands for the sum of the squares of the residuals. Then, by hook or by crook, or by using solver in LibreOffice, you would minimize the SSE by varying a fit and b fit. You can actually do the varying by hand, but it is a bit tedious, and it's hard to tell when you've got the best minimum, unless you do a lot of plotting of points, so it's easier to let solver do it for you. As mentioned, the link in the description is a video that explains doing nonlinear regression with a spreadsheet in more detail. Takeaways are: 1. The human eye is quite sensitive to straight lines, and plotting data to examine for a linear relationship is a powerful way to estimate the functional relationship between pairs of data. 2. A linear function such as y equals bx plus a appears as a straight line on a linear plot. 3. An exponential function such as y equals a times e to the bx or a times 10 to the bx appears as a straight line on a semilog plot. Four, a power log function such as y equals ax to the b appears as a straight line on a log-log plot. Five, there are many other relationships you can try to see if you can get a straight line. Thanks for watching. This video is brought to you by the DOFPro team.